Hello, Saurabh is again here, and this time our presentation is focused on hybridization scheme for Sp3 molecule. In earlier case, we had a discussion on the D3H symmetry, flat sp2 system. Now we are here with the sp3 case, and we will be talking about the hybridization that involves sigma orbitals. To be very specific, let's begin with the TD symmetry, tetrahedral symmetry with an AB4 type of molecule, and the methane molecule is a classical example of this kind. And it has a large number of symmetry operations, that is E8C3, 3C2, 6S4, and 6 sigma D. It's not hard to visualize these symmetry operations, and molecule appears to be quite symmetric. Let's see how we can visualize these symmetry operations. We have first a cube where all the atoms are inserted. So we have a central carbon atom, and the valencies are directed to the alternate corners of the cube. So this is the first carbon that joins hydrogen 1 or A, then this joins hydrogen B, hydrogen C, and the next one is hydrogen D. Now you can notice that the two valencies are opposite to each other. That makes a precisely bond angle of 109 degree 28 minutes. When you choose an axis for rotation, obviously it does not have a C4 axis, but instead it has a C2 axis. And as a consequence of C2, it is also having an S4 axis along the Z coordinate. So C2 and this S4 coordinations have been displayed here. And similarly, along the y-axis, you're going to have the same C2 along the y-axis, S4 along the y-axis, and so C2 along the x-axis and S4 along the x-axis. They can be visualized from this figure. Also, because each molecule has a C3 axis as a pyramidal kind of substance, if you visualize from that passes through carbon and hydrogen, one of the bond, you have C3A as displayed, that is going to give C31, C32. And similarly, as many hydrogen atoms are there, you will have as many number of the C3 axis here. And you can of course notice that it would also have a dihedral plane of reflection that would cut the two opposite hydrogens and carbons and reflecting the rest of the two hydrogen atoms. So this is how symmetry is constituted by a tetrahedral molecule. You have identity HC3. We have seen that for all the four hydrogen atoms, carbon-hydrogen bonds, we have C31 and C32. So it makes 8. Similarly, 3C2 along the XYZ plane that have been displayed, and S4 rotation that we have described in the very earlier video. And similarly, you have 6 dihedral plane you can locate by yourself. So this is the character table for tetrahedral point group at your Percival. Now, what next we are supposed to do is, we are supposed to find a basis for sigma bonding. And for that, as usual, we'll be taking care of the bond vectors. What we suggest is, if there are no shifted bond vectors, all are shifted, so it becomes 0. And each bond vector which is unshifted contributes to 1 that we have studied earlier. So in case of identity, because there are 4 bond vectors, the value is 4. But when you talk about the bond vector or C3, that is passing to one of the carbon-hydrogen bond and that remains unshifted while the rest of the 3 remain shifted. So for each of the bond vector, that's contribution comes 1. Or C2, of course, it's like a cube that is moved by 90 degrees. So it has 0, and so is the case with S4 0, and a sigma D would contribute 2 because it would take 2 bond vectors simultaneously reflecting the 2 hydrogen atoms. So we are in the position to develop the characters for a reducible representation or sigma bonding. So we have 4, 1, 0, 0, and 2 are the characters. If we do it, now the next thing is to decompose this using the standard reduction formula, and we'll see that how a reducible representation can be decomposed into corresponding irreducible components. And in doing so, what we'll do is, I will use the standard reduction formula as we have described, because there are 24 elements, and multiply them accordingly. You get A1 once. Similarly, the contribution of A2 comes out to be 0. For E, this value comes out to be again 0. For T1 also, the value drops to 0. However, for T2, the value is 1. So we have seen that there are 2 major contributing things. One is A1 and other is T2. That has to be there because we are talking about a triply generate p orbitals and a singly generate s orbital here. Well, even in all cases, the two bond vectors is equivalent to A1 plus T2, and A1 contributes for s orbital as we understand for TD point group. Then T2 would be corresponding to either Px, Py, or pz. There is another option that you can have dxy, dxz, dyz. You have to simply inspect the character table and to arrive at this conclusion. Obviously, because there is no d orbital or other d orbitals are of very high energy in the methane molecule, you are left with the only chance that T2 would contribute from px, py, pz, and therefore we would suggest that the hybridization in this molecule is not Sg3 but it is Sp3, and so is the case with the methane molecule. That is how symmetry becomes very important in deciding which kind of orbitals are involved. Not only that, it also lowers the quantum mechanical calculations, treatments, and all by using cell. In this video, we are not going in details with how cells are formed, but we will certainly finally the kind of equation that we have obtained would like to see. So the wave functions for hybrid orbitals can be represented as using the Salk as a symmetry adopted linear combination concept, and we have the sp3 first orbital that in terms of 2s, 2px, and 2py and 2pz that comes out to be all plus ones, and for another sp3 2 bond it is 2 minus 1 and plus 1. For the third one, you have plus minus minus minus, and the fourth one is of course alternative. It will go plus minus and plus minus. Accordingly, you can decide the nodes of the wave functions in that particular molecule. So this is a very interesting to work out. You can even work out by yourself because it's not quite difficult to see. And finally, we reach to these equations. So that's for now. We'll be talking about more in terms of applications of symmetry and group theory in chemistry in coming videos. Thanks for watching.